Here is a combined summary of the 2 pages. Graphs are fundamental data structures used to represent relationships in various domains. In network science, real-world graphs are globally sparse yet contain numerous pockets of high edge density. A fundamental task in graph mining is to discover these dense subgraphs, which has a rich set of applications in fields such as social sciences, bioinformatics, cybersecurity, and more. Most formulations of dense subgraph discovery involve finding a single or few optimally dense subsets. However, in real-world applications, one does not care about the optimality. Instead, we want to find a large collection of dense subsets that cover a significant fraction of the input graph. This paper introduces a new definition of regularly triangularic (RTR) families, which capture the notion of dense subgraphs that contain many triangles and have degrees comparable to the subgraph size. The authors design a provable algorithm, RTR extractor, that can discover RTR families that approximately cover any RTR set. The algorithm is efficient and inspired by recent results that use triangle counts for community testing and clustering. Experimental results show that RTR extractor has excellent behavior on a large variety of real-world datasets, covering a quarter of the vertices with subgraphs of edge density more than 0.5, for datasets with 10m plus edges. The authors also provide a theoretical framework for dense subgraph discovery, using triangle density as a guide. They define the notion of RTR sets and prove strong theoretical guarantees on algorithms. The empirical goal is not recovering RTR sets but discovering practical dense subgraph discovery algorithms. The paper demonstrates the utility of RTR extractor for unsupervised graph discovery tasks, correlating the output with meaningful sets of similar vertices in a citation network. The author's contributions include a new theoretical setup for dense subgraph discovery, accounting for triangle density, and the design of a provable algorithm, RTR extractor, that is extremely successful at finding many dense subgraphs in real-world datasets. The research paper discusses the problem of covering a graph with dense subgraph families, focusing on triangularic sets. The authors introduce a novel algorithm, RTR extractor, which outputs many sets that are dense and optimize for both internal triangle density and the degree regularity. The algorithm's primary utility is shown by its guarantees on the output, ensuring that every omega-1 regularly triangularic set has a constant fraction of its vertices in the output. The authors also discuss the importance of triangle density and how it implies edge density, making the algorithm efficient for finding dense subgraphs. The paper highlights the significance of the algorithm's results in real-world networks, demonstrating its ability to capture dense subgraphs effectively. The summary covers key points from both pages, including the definition of triangle density, the concept of regularly triangularic sets, and the guarantees provided by the RTR extractor algorithm. The paper discusses the RTR extractor algorithm, which is designed to identify dense subgraph families within a graph by leveraging triangularic sets. The algorithm iterates through an extraction process that removes edges and vertices, ultimately leading to the formation of regularly triangularic sets. The key insight behind this approach is that the neighborhood of a vertex in the cleaned graph is automatically rich in triangles, allowing for a simple BFSBASED algorithm to extract dense and triangularic sets. The analysis of the RTR extractor begins with 2 parts. First, it shows that the output of RTR extractor is omega-1 regularly triangularic. This is achieved by proving that the cleaning operation in step 5 removes edges that reduce triangle density, and that the degrees in the output set S are within constant factors of each other. Additionally, the paper demonstrates that a constant fraction of any omega-1 regularly triangularic set S is contained in the output of RTR extractor. In the well-separated case, the analysis becomes more complex as it requires arguing that there is a single extraction step that removes a constant fraction of S. This involves a careful examination of how vertices in S get deleted from the current subgraph H. The parameter beta plays an essential role in preventing many vertices of S from ending up in other extractions. The main argument revolves around the idea that only an extraction seated inside S can remove a significant part of S. The paper concludes by encapsulating the analysis as a lemma, which directly implies Theorem 3.5, This theorem states that a polynomial fraction of vertices of S is present in the family T, with all constants being polynomially related to each other. The proof of theorem 3.5 is also detailed, considering three possible cases for the seed vertex V of an output set T. V is in S, the neighborhood N, V, intersects S, or a vertex from S is added to T in step 13. Each case is addressed separately, utilizing the well-separated condition and the choice of epsilon and beta as alpha squared and alpha squared divided by 4, respectively. The paper discusses a novel algorithm called RTR extractor, which aims to cover a graph with dense subgraph families. It starts by covering a graph with dense subgraph families, focusing on triangularic sets. The algorithm's running time is analyzed, showing an upper bound of O, T plus, M plus N, ln, where T is the running time of triangle enumeration. The paper also presents experimental results on various datasets, comparing RTR extractor with state-of-the-art procedures like K-core decomposition, 2,3, nucleus decomposition, Louvain algorithm, iterated Charikher's greedy peeling algorithm, and flowless. The results show that RTR extractor significantly outperforms other methods in terms of coverage at high densities, especially in networks with high clustering coefficients. However, it lags behind in datasets with lower clustering coefficients, such as the DBLP citation network. The paper concludes that RTR extractor is a highly effective method for finding dense subgraphs in networks, especially in social networks and collaboration graphs. The research paper discusses a novel method for discovering dense subgraphs in networks. It presents a new algorithm, RTR extractor, which effectively covers a significant portion of vertices in dense subgraphs, outperforming other methods like Louvain and greedy. The algorithm's strength lies in its ability to extract dense subgraphs with high edge density, often missed by other methods. This is demonstrated through various datasets, including social networks, citation networks, and email networks. The paper highlights the importance of edge density in identifying meaningful clusters and criticizes the classic greedy objective for favoring large but sparse subgraphs. A case study on a computer science citation network showcases the algorithm's ability to uncover clusters focused on specific topics, such as spatial joins and object-oriented programming, without prior knowledge of the network semantics. The results are visually supported by figures and tables, providing a comprehensive understanding of the algorithm's performance and the significance of its findings. The paper discusses the RTR extractor algorithm, which is designed to identify densely connected subgraphs within large networks efficiently. It leverages triangularic sets to find dense subgraphs, with a focus on real-world networks. The algorithm's efficiency and accuracy are demonstrated through experiments on various datasets, including social networks and biological networks. The authors also present a detailed analysis of the extracted subgraphs, showcasing their relevance to the overall network structure. This includes visualizations using the Fruchterman-Reingold forced drawing method and radial illustrations of vertices by closeness centrality. The paper highlights that the RTR extractor algorithm outperforms other methods in identifying dense subgraphs, especially in cases where the subgraph is sparse or has a high variation in induced degree among vertices. Moreover, the paper addresses the issue of cleaning, which is crucial for extracting meaningful subgraphs. The authors emphasize that the cleaning procedure can be applied to other tasks beyond just dense subgraph extraction. They also discuss the potential for organizing the output sets of RTR extractor to provide a hierarchy of clusters, a concept that is not fully explored in the current work. The paper concludes by discussing future research directions, including the possibility of extending the RTR extractor algorithm to detect hierarchies within networks. It also points out the importance of further investigating the relationship between average case complexity and approximation complexity, as well as exploring other applications of the cleaning procedure. The paper provides a comprehensive overview of the RTR extractor algorithm, its implementation, and its performance in identifying dense subgraphs in real-world networks. It contributes to the ongoing research on community detection and dense subgraph extraction, offering insights into the potential improvements and extensions for future studies. Covering a graph with dense subgraph families, via triangle-rich sets, 66, Nan Wang, Jingbo Zhang, Qian Li Tan, and Anthony K. H. Tung, 2010. On triangulation-based dense neighborhood graph discovery. Proc. VLDB in Dow. 4, 2, 2010, 58-68. 67. Yichen Xu, Chenhao Ma, Yixiang Fang, and Zifeng Bao, 2023. Efficient and effective algorithms for generalized densest subgraph discovery. Proc. ACM Manaug. Data 1, 2, Article 169, 2023. 68. Bin Zhang and Steve Horvath, 2005. A General Framework for Weighted Gene Co-Expression Network Analysis. Statistical Applications in Genetics and Molecular Biology 4, 2005, Article 17.